So today's notes. Oh. Today's notes are about conductors and electric fields. So we've talked a little bit about this, but I'm grabbing my computer. So we've talked a little bit about it, but now we're going to talk in depth. We know generally what a conductor is versus an insulator. And we're going to look at how conductors respond to electric fields, which I've mentioned a little bit, but we're going to get some more specific examples, stuff like that. So, conductors and electric fields. In a conductor, in electrostatic equilibrium, none of the charges are moving. So that's the first key, is if you have a conductor and it has achieved electrostatic equilibrium, that means none of the charges are moving. Charges can definitely move in a conductor, unlike an insulator. But in a conductor, they're going to move very rapidly to achieve the following goals, as we'll talk about here. So the whole deal is most of the time, the charges are not moving. Does that make sense? And so generally, they're in what we call electrostatic equilibrium. So remember, equilibrium means everything is balanced, nothing's getting pushed around, and it's all good. So, the charges in a conductor are always free to move. If there's an electric field, they will move. Okay? Does that make sense? The charges are free to move, and if they are in an electric field, they will move. So if you take those two statements back to back, you have to realize what electrostatic equilibrium means. That if you're in electrostatic equilibrium, none of the charges are moving. And the very next statement says the charges are free to move. If there is an electric field, they will move. Which has to mean that if there is an electric field, they will move, then the conductor would not be in electrostatic equilibrium. So if the conductor is in electrostatic equilibrium, there is no electric field inside of the conductor. Does that make sense? Because if there was, then the charges would move. So that is the most important statement, probably from the set of notes, is the electric field is zero at all points inside of a conductor that's in electrostatic equilibrium. And most of the things that we're going to look at are conductors in electrostatic equilibrium. So pretty much any time you have this happening, you have zero electric field inside the conductor. So yeah, that's important to know. So whenever you guys get this, as you can see the picture here, like this shows a bunch of charges built up on the outside of this, random looking conductor. The key is the electric field is zero on the inside, because anything else would cause the charges to move. So like that. The reason why I spend a second on this is because you're going to have a lot of problems in this class. Find this, find that. One of the first keys you have to remember is the electric field inside of a conductor is zero. Okay? So I want you guys to know why it's zero. Because if it wasn't zero, then the charges would be moving. Any excess charge inside of a conductor must lie at the surface. Okay? Because again, if it was an excess charge inside the conductor, well then it would have an electric field coming out. That makes sense? And therefore it wouldn't stay there, it would be moved or move something else. Any charge on the interior would create an electric field, violation of our conclusion. So physically, the repulsive forces of the charges cause them to move as far apart as possible without leaving the conductor. That's why the charges build a ball on the outside. Everybody okay so far? So the electric field right at the surface of a charged conductor is perpendicular to the surface. So this is because all of those charges are built up on the outside. So they will have an electric field going off of the surface. And at every point, no matter what the shape of the conductor is, the If the electric field had a component tangent to the surface, it would therefore exert a force on the charges at the surface and cause them to move along the surface, violating our assumption that all charges are at rest. So, yeah. Let's be perpendicular in sequence. So the picture below shows a positively charged metal sphere above a conducting plate with a negative charge. So here we have our field lines. Do the field lines go from positive to negative or negative to positive? Field lines go from where to where? Positive to negative. And so for each one of these positive charges, you should be able to draw a field line to a negative charge here. So it'll end up looking something like this. Now note that, the first one comes just straight down, but then you have these other ones that kind of turn off and come down. You'll actually note that there's one more positive charge than negative charge, so then that positive field line just kind of goes off into space to try to find a negative to connect with. Does that make sense? As it says right here, these conductors are in electrostatic equilibrium, so the field is perpendicular to the surface. So notice it starts perpendicular from the sphere, it ends perpendicular to, or I guess rectangle if you want. It can do anything in between, but those field lines will be perpendicular at the surface. Okay? And when y'all do an upcoming lab, y'all are going to theoretically see all of this. I say see, because that's feels good. Screening our electric field. So if the electric field within a conductor is zero, well, the electric field within a conducting enclosure also has to be zero. Huh? Like if you have this metal conductor, you just cut a hole in the middle of it, well, that electric field inside there should also be zero for the same reasons. A conducting box can be used to exclude electric fields from a region of space. This is called screening. Metal walls are ideal for screening, but wire screens or wire mesh can also be used. So, screening has another term that's sometimes associated with it. It's called a Faraday cage. Some of you have heard of a Faraday cage, some of you haven't. This is what it's all based on. Now, ideally, you want a nice solid piece of metal and it works perfectly. But depending on the size, like if you're talking about, if you're thinking about like electric fields, metal meshes can be used for screening to make Faraday cages as well. But depending on the size of the hole in the mesh kind of depends on the effectiveness of it. Right? If the holes are generally pretty large, it's going to be difficult to screen quite as well. By screening, I mean it will have zero electric field inside of the conductor. Now it should be noted that we're talking about static fields, like unchanging fields. A lot of this works as well with a changing electric field. Okay? So, for example, if you have a cell phone, it works off of electromagnetic radiation, right? These EM waves traveling through space. If you put that phone inside of a metal conductor, no waves will go inside of that metal conductor. It will block all of it. And anything that's put off will also get screened out as well. So if you put, think about just, if you had like a metal bowl, like two metal bowls, you stick your phone in there, close it, it would not receive any signal. Does that make sense? But that's a wave. It's changing with time. So it's not exactly the same as this, but it basically still works if it's a solid conductor. If it's a mesh, it works pretty well, but the mesh works less well depending on the size of the wave, the frequency that the wave is changing with, and the size of the holes in the metal. So if you just take some metal mesh and wrap it around your phone, it may or may not perfectly screen it. But it's pretty close. So even a rapidly changing wave is still effectively screened for the same reasons here. Because basically what happens is that wave goes in to hit your phone, But instead, it's that cage that goes around the cage and passes, and so it can't find it. And so that's how Faraday cages work. If you see pictures of Nikola Tesla near his Tesla coil that he made, that he didn't make small ones. You'll see him, he's just like sitting there like reading a book, like completely unconcerned, because he's also inside of like a Faraday cage. Because he understands that like these large fields might want to strike at him, but like they have to go around. Just to be straight. And so like I said, it's less effective, you know, with mesh, but it's the same concept. And so we'll look at some of that stuff, you know, as we get down the road here. Conductors and charge distribution. So, any excess charge in the conductor will be found on the surface. It may not be uniformly distributed. Right? If it's a nice, even surface, like a sphere, then sure, all of the charge will be evenly distributed on the surface. But basically, unless it's a nice sphere, the charge will gather at different points. At sharp points, the density of the charge is higher, and therefore the electric field is stronger. So this uneven distribution of charge is because there's no net force from one charge on another, and the field still comes off perpendicular to the surface. And so this seems a little counterintuitive, because you're like, well, these charges here are further apart than these charges here. Shouldn't these guys repel each other? And the answer is no, because there's no net force on the charges on the surface. Because if there was a net force on the charges on the surface, then they would move. Which is why they tend to gather at points. And so if you have things like, you know, anything with a corner, like a square or rectangle, you're going to have a bunch of charges gathering at that point. Which makes sense from like a surface area kind of statement, because if you think about it just like a flat side, you're like, okay, there's a lot of space here, so they can all kind of spread out. But as you get towards the corner, well, they, you know, all kind of just bunches up there. So it makes some sense, but it's kind of weird to think about, at least for me. And so if you remember back when I had that Van de Graaff out, like last week, remember that was? And y'all were like trying to poke me with your finger, and I said that doesn't work very well. And it was easier to like fist bump to see something. The flat surface allows the charges to be further apart, because when they gather up like this, they're actually able to ionize the air, and they're actually able to come off into the atmosphere instead of just like staying on the surface. The reason why they're able to ionize that is because you'll have more charges in a smaller area, which will increase the electric field in that area, which will actually cause ionization of the particles around it, if the electric field is strong. So that's why you don't tend to see much when you go finger to finger, because the electric field tends to be strong at points. So the electric field near very sharp points may be strong enough to ionize the air around it. Said, the lightning rod has a very sharp point, so that if a building is beginning to accumulate charge, meaning a lightning strike might be imminent, the large field develops at the tip of the rod. Once the field ionizes the air, the excess charge in the building can dissipate into the air, thus reducing the electric field and reducing the likelihood of a lightning strike. A lightning rod is intended to prevent a lightning strike. Now, can lightning rods be struck by lightning? Absolutely. And they're also more likely to be struck because they tend to be higher up in the air, and because they've ionized the air around it, thus making it a nice channel for the lightning to travel through. So, overall, they do reduce the number of lightning strikes, but you know, if you go from, say, 100 lightning strikes to 50 lightning strikes, that's good, it's a reduction. But if you were just standing there and you watched this building get struck by lightning 50 times, you go, it's getting struck by lightning a lot. So it's like, yes, it is, but you'd have to know how many lightning strikes would have happened without it, which, you know, you can't really see that. But in general, they tend to reduce lightning strikes, but also lightning rods tend to be grounded, like literally attached to the ground. So even if it gets struck by lightning, well, all of that energy just goes into the ground. And so typically lightning rods aren't just grounded with like a small tiny wire. They have big fat conducting wires just in case they do get struck by lightning. Because that's one of the biggest dangers with lightning, is that it will strike something and then not all travel to to the ground together. The problem is like when lightning strikes a house, it tends to like hit that and then, find like a pipe and go into the ground. But the problem is if it hits that, decides, half of it decides to go left, well, that may not be the shortest path to ground. So, anyway. So, the Earth has an electric field. The Earth, on average, has a charge of negative 570,000 coulombs, which is a lot. So remember, 1 coulomb of charge is a dangerous amount of charge. The Earth itself has basically 570,000 extra coulombs. So this is about 3.56 e to the 24th electron. So the 24th has about 3.5 septillion electrons extra. We don't typically notice this charge. You guys notice it? Not really. You don't notice it for a few reasons. Number one, you have the same potential as the Earth. So even though the Earth has this, quote, voltage or whatever, well, you're on the Earth, so it's the same. So think about, standing on the side of a mountain. The height doesn't kill you. You're just there. And unless you see like a big hole next to you, you don't notice that you're up that high, really. When you start talking about atmosphere, but we're not into that. Things like thunderstorms have much larger fields than this. Okay? So the thunderstorms, the reason why they have larger fields is not because they gather more charge in that, it's because they gather more charge in a smaller area. Because really the answer is, this may seem like a lot of electrons, but if you have this many electrons spread out over the whole surface of the Earth, Earth is kind of big. And compared to this many extra electrons, that's a lot of electrons. Like if you put that many electrons on a person, that would be crazy. But compared to the surface of the Earth, it's not. So this would be like giving each atom in 10. So it's like giving each atom in 10 sheets of paper 1 extra electron. So if you have 10 sheets of paper, you give every single atom in there 1 extra electron, that is how many extra electrons you have. Then if you kind of think about like distributing 10 sheets of paper, cutting up in little bits, evenly over the surface of the Earth, you kind of realize like that's basically nothing. So it seems like a large charge. And the whole reason why I bring this up is because the Earth does have a net charge, which I think is an interesting fact, but we don't really notice it at all for many reasons. So overall, we do lose some electrons into space, but we also gain some from the sun. And so overall, it kind of balances out, but then we also get electrons from other cosmic sources. So overall, we tend to lose as many electrons as we gain. Is it always 570,000 or negative 570,000 coulombs? No. It comes and goes. But overall, it's big and it's negative. But again, the Earth is kind of big. Under normal circumstances, the Earth's electric field outdoors near ground level is a uniform field, about 100 newtons per coulomb, directed down, because it's negative. Right? What is the electric force on a free electron in the atmosphere? You just have an electron going around. And what acceleration does this force cause? So to find the force, well, F equals QE. Well, that's E. So what's the charge on an electron? Some number. Yeah, it's over there on the wall. So here's our picture here. So we notice that the field is down. So we can just do F times QE. That will give us the magnitude. But again, does that give us the direction? No. And as indicated by this picture, what's the direction? Because it's negative and the Earth is negative, so it'll go the other direction. You okay with that? Yeah. Okay. But it takes a second to think about it. So here to find the force, you just plug that in, 1.6 times 10 to the negative 19 coulombs. So yes, that's a force. Is this a very large force? It's a very small force, but electrons are very small, so we go, okay, what's the acceleration? Well, acceleration is force divided by mass. We take that tiny force divided by the tiny mass, and we get a acceleration of 1.76 times 10 to the 13th meters per second squared. 10 to the 13th, it's a little over, what is that, 17 trillion meters per second squared? Yeah, it'll cause electrons to go up. This is one of the reasons why we lose electrons to space, because we have a bunch. Now, do all of them get that velocity all the way up? No, obviously, as you get further from the surface of the Earth, you get weaker electric field. You know, then a thunderstorm comes along, or an oxygen molecule will come along and snatch up that electron, whatever. Many things can happen. All right, a proton is moving to the right in a vertical electric field. A very short time later, the proton's velocity is, so here it gives us the original velocity is there, and it's in an electric field that's vertical upwards. So what is the proton's velocity a very short time later? A, B, C, D, E. C. Okay. Yeah, it could be B. But it's definitely not A, D, or E. You know. So here's the key. If I was debating between B and C, it says a very short time later, so I'd say, it goes up a little bit. All right. Which electric field is responsible for this proton's trajectory? So let's say all you see is a proton, and you see it come over here and go. Which electric field caused this? Did A cause it, B, C, D, or E? So first of all, is A, B, C, D, and E all legal fields? Well, it hasn't crossed yet. So. Thus far, they are all okay. So we haven't eliminated any just because they're done. So which one do you all think? Sure. Possibly B. Okay. Anything else?
It's probably wrong, but I think it's E.
E?
I'm probably wrong.
I'm guessing E.
Yeah, what direction is it going?
Well, you have this trajectory.
The arrow.
Well, you also get the word parabolic.
Probably blue.
No, what? What?
Okay, think about this. If I take a ball and throw it through the air, they'll have a parabolic trajectory. What direction is the gravitational field? It's straight down. So in this case, if you take down and turn it to the side,
Bro.
you can see.
What was it? It was coming,
It's going like think about somebody threw it like over here.
Yeah.
They threw it up and it comes down.
Okay.
So that's the key, is that it's parabolic. Because if it's parabolic, what that means is that you have a component that's not changing. Does that make sense? So like you have the component that's perpendicular to the field would not be changing. Because if it's perpendicular, the field can't move it that way. So like if you think about just throwing a ball through the air, the whole reason why you get a parabolic trajectory is like if I throw a ball up, you can split its velocity into an X and Y component. The X doesn't change. The Y goes up to 0 and then falls down. But X stays constant. That's what gives us our nice parabolic line. Alright, so that's the key. Is like I know it's not a whole lot of information, but it says parabolic, so you got to remember. And here's the thing: they love to do crap like this. When I say they love to do crap like this, like I saw this one problem. It was like a physics C problem. It's like electric fields, and it's like, oh, you got this electron within this field. It gives you like all these numbers, and you just start cranking on it. But then like part like E or something is like, okay, calculate its acceleration, and you have to take like 2 derivatives to get there. And when you get there, like the acceleration is like 9.83. You're like, wait a dang minute. Like it's funny because like the whole time you thought you were doing like electrostatics, but no, it was just all projectile motion. It's like, oh, I hate it.
That is wrong.
So force versus torque. All right, so you guys learned about torque last year. Force is a push or pull, torque is a twist. So here, the key is that if you have something, so it says like an electric dipole, it has the same amount of charge on both ends, right? The total charge is zero, right, net charge. But you'll have positive, say, on one end and negative on the other. Well, the net force will be zero because the net charge is zero. But just like torque, like when you turn something, a dipole in an electric field will turn, right? Now, this is a little different than the normal turning because the electric field doesn't tend to move as your object moves. So it says right here, there's net torque on the dipole with a uniform electric field, which causes it to rotate. The equilibrium position of a dipole electric field is when the electric dipole aligns with the field. So here, let me write on this. No, I don't want to. Okay. So here you can see I have a positive charge and a negative charge. So if we're just focusing on this dipole, does the field go from positive to negative or negative to positive? Right? So this field will go from positive to negative, right? So the dipole moment, so it says, okay. So just kind of read through this first. So because the forces on the positive and negative charges are equal in magnitude but oppositely directed, there's no net force. We already talked about that. Then it says, however, there is a net torque on the dipole that causes it to rotate. So if this is a positive charge, it's going to want to go up because of this field, and the negative charge is going to want to be pulled down. Right? So here you can kind of think of it like if I have this, you know, the field between these two goes from positive to negative, right? But like a full loop would go, you know, all the way around. So maybe I'm going to go with that. I'm going to stop that. So here, this thing wants to go up, this one wants to go down. The net force is zero, right? Because this force equals that force. But it will cause it to rotate. So in an ideal situation, it will rotate up to end up like this, right? Positive is up, down is down, and they end up canceling out, so no movement happens. Does that make sense? So it's just, it would ideally, like, you turn on the field, let's say you have this guy sitting there, you turn on the field, it just turns straight up. Now, overall, if you gave it enough time, that's what would occur. But you also have objects in motion, which tend to stay in motion. And so what ends up happening here is that it'll rotate, but when it gets straight up to this point, well, it's an object in motion, so it'll actually rotate past that point. And then the field will have to slow down, stop it, and then push it back. And so it kind of wobbles until, you know, it has enough energy to decay off of it, so it sits straight up. Now, in most situations, are these molecules given enough time to do that? Probably not. But it could rotate and stop perfectly aligned with the field. Does that make sense? Now, it doesn't take that much time, but most of these fields aren't. They might be strong enough to rotate the molecules, but they're not big enough. Because, you know, molecules tend to move at a pretty good speed. So I'm not saying it can't stop that way, but it tends to do that. And so here, what this is saying is that we have what's called a dipole moment. It's a vector that points from the negative to the positive charge, right? And so we use this dipole moment. We're not going to use it too much in this class because we don't do too much rotation. But when you think about rotation, like torque is R cross F, right? So you do like R has like this dipole moment here. F is the force on the positive charge, and then you can calculate the torque, right? We're not going to do that because it's like all like, I mean, how big is a molecule? Anyways, so when the dipole lines up with the field, the net torque is zero. The dipole is in static equilibrium, and we can say the dipole moment tries to align itself with the field. So even not thinking about torque, it makes sense because we're trying to get the molecule is trying to get its little field lined up with the external, I should say. It's trying to get its moment lined up with the external field. Does that make sense? So it wants to turn and sit that way. A lot of your problems, if it involves molecules with the It'll be things that happen, you know, as molecules are like moving through a field. So let's take a look at some examples. So here, a dipole is held motionless, so it's being forced here. When the dipole is released inside of this electric field, which of the following describes the subsequent motion? So it moves to the right, moves to the left, rotates clockwise, rotates counterclockwise, or it doesn't move. Yay.
So like the first one you got right today.
Let's go. Means you learn, right? So it's not going to move, right? Because the positive charge wants to be on that end, negative is on that end, net force is zero, not going to. Cool. How about this guy?
Okay, it's gonna go like counterclockwise. Because the negative wants to go to the left and the negative wants to go away.
Positive wants to go this way, negative wants to go that way. So it should just rotate but not actually move. Right?
Right.
So the reason why I talk about it, you know, not stopping and continuing past that is because you'll get problems like that, but like that problem, did it say anything happens after this point? Like no, it's just look, where's it going initially? Right? Which dipole experiences no net force in the field? A, B, or C?
All of them?
All of them?
Yeah. Oh, go back to C.
Because yeah,
Oh, I
there's
see.
no net force because the dipoles. Yeah. Now some of them have a torque, yes, but they should all have zero net force, right? Now, which one experiences no net torque?
Wait, no. G.
They all
I'm thinking G.
Like here. There.
Oh, that's what's killing me.
Okay, so first of all, I think A is obvious it's going to rotate. B, less obvious, but still going to rotate. What's the deal with C?
Because when you see when I flip around,
Yeah, C would want to flip around, but here's the deal.
oh, but it's next to.
Well, no, it's perfectly aligned or anti-aligned with the field, as we would say. So it has no reason to rotate at this point. Like there's no net force here, right?
Yeah.
There's no net torque because torque is, you know, you go from the center
So it's
to
like,
this point here and then multiply it like,
like in between the field?
well, think of it like balancing a pencil.
Yeah.
Like you can balance something on the tip, not this thing, the tip actually moves, but you can balance something on your finger, right? Now when you get it balanced, there's no reason for it to go one way or the other. But it could easily fall over. And that's what's happening here. Is it's completely upside down. It's balanced. It has no reason to move. But, you know, if something comes along externally and gives it a little bump, well, then it's going to fall. Does that make sense? So this, like C is what we call anti-aligned or anti-parallel, because it's exactly upside down, but there's no net torque on it, for the same reason why there'd be no net torque when it goes the other direction. However, you know, like I said, it's perfectly balanced. How long is it going to stay that way? Who knows? But it just happens to be balanced. All right, conductor versus an insulator. Now this is important. So first of all, do you see these graphs? So in this graph, we have a electric field on the y-axis, and we have the distance on the x-axis. Okay. So in these cases here, we would say that we have something like a sphere or whatever, and our distance starts at the middle of the sphere and goes out. Okay. And so it says the graph of the electric field on a conducting sphere with charge Q would look like this, right? And then it says the graph of the electric field on an insulating sphere with a uniform charge distribution would look like that. So first of all, let's talk about the conductor. So we're looking at the conductor here. It says you just have this metal sphere. So whether it's hollow or completely solid metal, it doesn't matter, because all of the excess charge would build up on the outside. Does that make sense? Hollow, not hollow. It doesn't matter because all of the charge builds up on the outside. So how does that look at our electric field? So if we're starting from the center of this thing and going out, right, this is our distance, Well, this, from here to there is the radius, right? And so that's this big R, so I just want to use big R. That makes sense? And it's just using R for distance. So here, inside of the sphere, there is no electric field. Did I say that? Zero electric field. Then as soon as you hit that surface, boop, you go to the outside surface, you get maximum electric field, right? But then as you move away from the surface, it decays away. And that makes sense because our electric field is equal to KQ over R squared. So this decays is 1 over R squared. So the thing is what you should realize is like at this point right here, like if you just kind of ignore everything that was happening before, this looks identical to a point charge. So when you're outside of this, and let's say this thing has a charge of negative 10Q on the sphere here, if I put that negative 10Q just at this point, after here, the graphs would look exactly the same, whether it's distributed on the surface or all just concentrated at one point. Because once you get outside the sphere, it just acts like a point charge. Does that make sense? Inside the sphere, no field. Outside the sphere, this one. So like if I had a point charge to compare this to, blue. If I had the same graph here, but I had all of it concentrated at this point, basically the charge would go from infinity down to this. Right? Because you'd have like almost infinite electric field if you were at zero distance away. Right? And so this is just like the regular one, but it just kind of gets cut because of the surface of the sphere. So there's no electric field inside. And whatever its maximum is right there on the surface. Does that make sense? Okay. It's just think of like an electron. Because electron is a point of charge. Does that make sense? So this is like this stuff here in blue, that's what the graph of an electron's field would look like. And so what I'm saying here is that we're comparing the electron's field to like, say, this random number. Make sense? Okay. So now, if we look at an insulator, remember an insulator, the field can be anywhere. So the actual graph for an insulator will depend on the actual charge distribution, but here it says it's a uniform charge distribution. So we're going to assume, there might be some charge on the outside, but there's also charge everywhere inside. And so this leads to an interesting difference here, because it'll be zero in the middle, because you have zero distance, right? There's no charge. So if you go out to say like this point right here, let's say half the radius, that would be, so if we go like half the radius there, do y'all see that? If we go to this point here, we've gathered some charge inside of that circle that I've made, or sphere in the 3D. And so that corresponds to this charge level here. And so it's going to be linear, because as you go away from the center, you're going to get more and more charge inside of your little surface, okay? Up until the point where you hit the actual surface, right? At that, you've gathered all of the charge, and so you've reached your maximum electric field, and then it will just decay as, 1 over R squared when you get outside. Does that make sense? So you guys are going to get a few graph problems, not nearly as many as you would in, say, C. But one of the keys here is it'll ask you different questions. It'll be like, okay, what's the electric field in like region A? What's the electric field in region B? And if you realize like, oh, A is 0, okay, move on to the next part of the question. Or if it's an insulator, well, then you have to do a few calculations. Okay. So question 9. We have an electric field that has 20,000 newtons per coulomb to the right, causes a 2-gram ball that is charged 25 nanocoulombs to hang at an angle. What is theta? So,
Time to work this out.
What is theta?
yeah, you should have time.
Like, what is data in general?
What's the
The
angle?
idea. The idea.
So here, what I would do is bust out your net force. So you you get a free body diagram. So we've got gravity pulling this ball down. You've got the electric field pushing it this way. So F sub E, F sub G, and then the force of tension. Right? And those all should add up to 0, which means that you have a component here, F sub T of X, and you have a component here, Ft sub Y. And then Ft sub Y should equal Fg, and Ft sub X should equal Fe.
What's FT from?
Force of tension?
What's the?
Oh, tension.
Right.
Okay.
We can limit that one.
Okay.
Okay, so, we know the mass of our object here, so we can find the force of gravity, and from the force of gravity, we can find the force of tension Y, because they're the same. And from the force of tension Y, can we find this angle? Not exactly. In order to find the angle, we need at least two sides, or a side and two angles. I know this angle is 90, right?
Yeah.
So I can either find this angle, which is not going to be terribly helpful, unless you sign up correctly, but I mean, we need at least two sides. So that's how I find force of gravity. How do I find electric field?
Right there.
Sorry, how do I find electric force? Is what it is.
That.
That times what?
25.
Yeah. So remember, Fg is mg, right? Which equals force of tension Y. And Fe equals QE equals force of tension X. Right? Yeah, charge times the electric field. So here, the mass, in this case, is 2 grams. How many kilograms is that? 0.002 kilograms times 9.8 or 10, whatever you want to call it. It'll be fine. And then the charge on an electron is 1.6 e to the negative 19, right? Sorry, that's not it. That is the charge on an electron, but it's not charged up with that. How much is it charged? 25 e to the 9 coulombs, times our electric field of 200,000. Okay. So then you should get a number and a number, right? And then you take those two numbers, and I would use probably inverse tangent. Tangent inverse of opposite over adjacent, okay? So what I think is really interesting about a problem like this is it's technically a electric field problem. How much about electric field do you really need? You need F equals QE, right? I mean, everything else is stuff from like last year. So this is one of the reasons why at the beginning of the year, I need to go through that whole Newton's law review thing, which was fun, because it doesn't really go away. I'm not going to bother calculating these. These should be on here. Magical. Like I even use 9.81 next to me on that. So you should get about 14.3 degrees, maybe a little more or less, whenever you use 10 or something. That's essentially what you're going for there. Man, I really went off right turn. That was a completely different way of solving it. But in the end, you do tangent inverse of opposite over adjacent. I'm looking at it going like, why did I pick to do that? It must have been something the college board did, and I was like, fine. I don't mind doing that. I just think it's weird to go sine and cosine. I mean, sure, whatever, okay. That's just not something I think I would ever do. But then again, it's been a couple of years. I still don't think I would have done that. Whatever. Okay. thing, the enzymes cut it up, then in the solution, the fragments will have a negative charge. Then you take drops of the solution, the DNA fragments, place the wells at one end of a container of gel. So you end up with this container of gel, you place little samples of your DNA here, and then you put electrodes on it, positive on one end, negative on the other. So you put the negative by the end that you start at, because these guys are negative. And then the DNA fragments will move through the gel to the other end. What's interesting is that the rate at which they move actually depends on the size of the DNA fragment. And the reason why it depends on the size of the DNA fragment is because it's physically moving through gel, and it's experiencing a drag force, similar to like if you jump out of a plane, like the air resistance you feel on you is subject to the density of the air. But it's not just the density of the air, it's also the shape that you present to the wind and your mass. And so it's a very similar calculation, not that we've ever done a calculation like that in here, but it's a similar thing that happens here, that like if you leave them long enough, they should make it all the way to the other end. But you don't leave them on forever. And so what ends up happening is things that have, essentially smaller surface areas go further in the gel the same amount of time. And so they exert a force on the DNA, so you have this electric force, dragging this thing across there. And so the electric force is subject to the size of the electric field, but everybody gets the same electric field. So the real key difference here is they have different charges. And so different charges will actually get different forces from the same field. And so this is kind of what it looks like. This is obviously a drawing, but here you would have like your well samples here, and they kind of drag out, and they get separated as they go out, the different pieces of DNA. And so what's interesting here is these drag forces cause fragments of different sizes to migrate at different rates. After some time, the fragments sort out into distinct lines, creating what we call a genetic fingerprint. Two identical DNA samples would produce the exact same fragments and therefore have the same pattern, because they would be cut by the enzymes in the exact same way. And so what's interesting here is that if you do all this with different DNA samples, you'll get different, like these little lines here. This is the fingerprint. And so what's interesting, if you do it the same ones, you get the same fingerprint because they end up being drugged the same amount. And so this is a way to DNA test something, right? It's not the new fancy way, but that's essentially how you could, compare two genetic samples without actually looking at the molecules. Okay. So, not terribly useful in here, but if you did this in here, we're not going to do this live because that's way biology. But like I said, Tito, her class does it. So if y'all had AP Bio last year or the year before, or if you have it this year, what's up? Well, I remember it because last year is the first year I actually went into her lab and saw her students do it. So it's funny because they have the equipment and all that stuff. Okay, so that's the end of the notes. So that's just a little biology connection there. Not terribly difficult notes today, but I'd say they're not difficult from the what do you call it?